January 7th, 1941. Charles E. Sorensen sat alone in room 312 of the Coronado Hotel in San Diego, surrounded by hotel stationery and mechanical pencils. Outside, California's winter rain drummed against the windows. Inside, this 60-year-old production engineer was attempting something that every aviation expert in America had already declared impossible. He was designing a factory to mass-produce four-engine bombers using automobile assembly line techniques. A factory that would build planes faster than traditional aircraft manufacturers believed physically possible. The aviation industry's leadership had spent the previous day explaining to Sorensen why his employer, Ford Motor Company, should stick to making engine parts and wing sections. Leave actual aircraft construction to professionals who understood the craft, they'd said. Sorensen had listened politely. Then he'd returned to his hotel room and started sketching. By 4 a.m, he had covered 17 pieces of Coronado Hotel stationery with penciled diagrams showing how to break a 30-ton, four-engine bomber into sub-assemblies that could be manufactured simultaneously and joined together on a moving assembly line. The aviation establishment's certainty that mass production couldn't work for complex aircraft rested on apparently sound reasoning. A consolidated B-24 Liberator bomber contained approximately 450,000 individual parts. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. 360,000 rivets, in 550 different sizes, held those parts together. The aircraft stretched 67 feet long, with a 110-foot wingspan. It weighed 36,000 pounds empty. Traditional aircraft factories employed master craftsmen who hand-built each plane over weeks or months, custom-fitting components, adjusting tolerances, treating every aircraft as a semi-unique creation. This approach had worked since the Wright brothers' time. Why would anyone imagine it could be revolutionized overnight by an automobile man who'd never built an airplane? But Sorensen had spent 35 years perfecting something the aviation industry had never seriously considered applying to aircraft production. The Ford production system, the moving assembly line philosophy that had transformed automobile manufacturing from a craft into an industry. While aircraft manufacturers built their products the way medieval artisans had forged armor, one piece at a time with skilled hands, Sorensen saw bombers as just another manufactured product waiting to be systematized, broken into repeatable steps, and produced by workers who could be trained in weeks rather than years. The mathematical logic seemed straightforward to him. If Ford could build 15,000 automobiles daily across America, each car containing 15,000 parts, then building heavy bombers with similar techniques simply required scaling up the process. The fact that nobody had done it before didn't make it impossible. It made it necessary. The meeting at Consolidated Aircraft's San Diego facility the previous day had only reinforced Sorensen's conviction that revolutionary change was required. He'd watched Consolidated's workers assembling B-24 bombers outdoors under the California sun, working from sketches and templates rather than proper blueprints. Major components were custom-fitted to each airframe. Structural steel fixtures warped in the heat, making it impossible to produce two identical aircraft without extensive hand adjustment. Consolidated was managing approximately one completed bomber daily using these methods. The United States government needed thousands. The mathematics of that gap revealed why Sorensen now sat awake at 4 a.m, designing an entirely new approach to aircraft manufacturing. The context that drove this midnight engineering session had been building for months. President Franklin Roosevelt had announced in May 1940 that America must produce 50,000 combat aircraft within 12 months to confront what he called the approaching storm of global war. That number exceeded the total of all planes built in the United States since the Wright brothers' first flight at Kitty Hawk in 1903. Roosevelt wasn't being rhetorical. He was responding to the collapse of France and the apparent imminent defeat of Britain. German bombers were hammering London nightly. The Luftwaffe had achieved air superiority over Europe. If Britain fell, America would face Nazi Germany alone across the Atlantic, with an air force that ranked behind Romania's in size and capability. The Army Air Corps desperately needed heavy bombers, long-range, high-altitude aircraft capable of striking deep into enemy territory, carrying massive bomb loads, and defending themselves against fighter attacks. The B-17 Flying Fortress and the B-24 Liberator represented America's best designs for this role. Boeing's B-17 had been in limited production since 1937. Consolidated's B-24 had first flown in December 1939 and showed superior range and bomb-carrying capacity. But Consolidated aircraft lacked both the facilities and the manufacturing processes to produce B-24s at the scale Roosevelt's directive required. Traditional aircraft production simply couldn't scale fast enough. Consolidated's San Diego plant employed master craftsmen who'd spent years learning their trade. Each B-24 required approximately 6 weeks of assembly time using conventional methods. Training new workers to traditional aircraft building standards took years. America didn't have years. The War Department had initially approached Ford about manufacturing B-24 components, build wing sections, they'd suggested, maybe engine mounts, ship them to Consolidated or Douglas Aircraft for final assembly. Let the professional aircraft manufacturers handle the complex work of putting complete bombers together. Sorensen's boss, Ford Motor Company President Edsel Ford, had traveled to San Diego with him to inspect Consolidated's operations and discuss the component manufacturing proposal. What both men had seen convinced them that building sub-assemblies for someone else's inadequate production system made no sense. If Ford was going to enter aircraft production, it would build complete airplanes using Ford's proven mass production techniques, or it wouldn't participate at all. The decision represented either visionary confidence or spectacular arrogance, depending on which aviation expert you asked. Most asked tended toward the arrogance explanation. Dutch Kindleberger, president of North American Aviation, and one of the industry's most respected figures, summarized the prevailing view with dismissive clarity. "You can't expect a blacksmith to make a watch overnight," he'd told reporters when Ford's ambitions became public. The comparison seemed apt to aviation professionals. Automobiles, even complex ones like Ford's V8, contained perhaps 15,000 parts and weighed around 3,000 pounds. The B-24 Liberator contained 30 times as many parts and weighed 12 times as much. Building cars and building bombers were fundamentally different enterprises, requiring fundamentally different expertise. The skeptics had reasonable concerns beyond just complexity. Aircraft manufacturing required precision tolerances far tighter than automobile production. Wing structures had to be perfectly balanced. Control surfaces needed exact aerodynamic shaping. Engines and fuel systems demanded leak-proof connections that would function reliably at 25,000 feet altitude, where temperatures dropped to 40 degrees below zero and air pressure fell to 1/3 of sea level values. Moreover, aircraft designs changed constantly as combat experience revealed necessary improvements. The Army Air Corps modified B-24 specifications monthly, sometimes weekly. Traditional aircraft factories could adapt to these changes because their craftsmen understood the entire airplane and could improvise solutions. Ford's assembly line philosophy depended on fixed designs and standardized processes. Every worker performed one specific task repeatedly. Design changes meant retooling expensive machinery and retraining thousands of workers. How could mass production possibly work when the product kept changing? Sorensen's hotel room sketches provided his answer. Don't treat the B-24 as one aircraft, treat it as 11 major assemblies: the fuselage, the wings, the tail section, the bomb bays, the landing gear, the engines and their mounting systems, the gun turrets, the fuel system, the electrical harness, the hydraulic controls, the cockpit assembly. Build each major assembly simultaneously in separate areas of the factory, using dedicated production lines. Further break each major assembly into sub-assemblies. The wing, for instance, wasn't one component. It was the center wing section, 2 outer wing panels, leading edge assemblies, trailing edge sections, aileron and flap systems, fuel tanks, and landing light installations. Manufacture all sub-assemblies in parallel, using specialized workers and dedicated machinery. Then bring the completed sub-assemblies together in final assembly, where they'd be joined into major assemblies. Finally, marry the major assemblies on the main production line to create finished aircraft. The approach meant that while one B-24 moved down the final assembly line, hundreds of sub-assemblies for future aircraft were being manufactured simultaneously throughout the factory. Traditional aircraft production was sequential. Everything happened in order. Sorensen's system was parallel. Everything happened at once. The production speed this enabled seemed almost magical, but the mathematics were straightforward. If building one complete wing required 600 worker hours using traditional methods, and if you had 600 workers each performing one specialized task for 1 hour, you'd complete the same wing in 1/60th the time. Scale that logic across the entire aircraft, and suddenly building one bomber per hour became not just possible but inevitable, given sufficient factory space, enough specialized machinery, and adequate numbers of trained workers. The sufficiency of those three requirements would prove to be the central challenge, but at 4 in the morning on January 8, 1941, Sorensen believed he'd solved the theoretical problem. His sketches showed a factory approximately a mile long with 2 parallel assembly lines. Raw materials and prefabricated sub-assemblies would enter at one end. Completed B-24 Liberator bombers would roll out the other. At breakfast with Edsel Ford that morning, Sorensen was, as he'd later write, somewhat woozy from lack of sleep, but carried away by enthusiasm for the project. He showed Ford the sketches and outlined what he was calling the bomber an hour proposition. Edsel Ford, who would carry the massive stress of this project to his grave just 2 years later, immediately grasped both the audacity and the necessity of the plan. Ford Motor Company would build such a plant, Edsel assured him. They'd spend whatever it took. They'd solve whatever problems emerged. They'd prove that American industrial capacity, properly organized, could overwhelm any enemy through sheer production volume. An hour later, both men sat in Major Reuben Fleet's office at Consolidated Aircraft Headquarters. Fleet, the company's founder and a former Army aviator, listened to Sorensen's proposal with visible skepticism turning to outright dismissal. Build one bomber per hour, using assembly line techniques, with workers who'd never built aircraft before. Fleet's response was polite but firm. Ford could certainly build components, for Consolidated to assemble. But the idea of mass-producing complete B-24 bombers using automobile factory methods was technically impossible, organizationally impractical, and conceptually misguided. Sorensen didn't argue. He simply noted that Ford Motor Company wasn't interested in being a parts supplier. If Ford couldn't build complete aircraft, it wouldn't participate at all. Then he and Edsel Ford returned to Michigan to begin construction of the largest aircraft factory in history, based on sketches drawn on hotel stationery by a man who'd never built an airplane. The site selected was 1,878 acres of farmland, owned by Henry Ford, near a creek called Willow Run, about 30 miles west of Detroit, near Ypsilanti, Michigan. The property had housed a summer camp where teenagers learned work ethic through farming. Those farm fields would now become the world's most advanced aircraft manufacturing facility. Construction began in April 1941. Albert Kahn, the legendary industrial architect who'd designed dozens of automobile factories, translated Sorensen's sketches into actual building plans. The main structure would be L-shaped, forced into that configuration by property easement issues with adjacent land. The scale was unprecedented, 3.5 million square feet of factory space under a single roof. The main assembly building stretched more than half a mile long and a quarter-mile wide. 2 parallel assembly lines would run the building's length. 65 acres of factory floor would be covered by one continuous roof, supported by columns spaced to allow aircraft wings to pass between them. The building would require more concrete than Hoover Dam, steel framework equivalent to constructing a battleship. Electrical systems to power an entire city. Climate control to maintain precise temperatures for aluminium forming operations. Rail lines to bring in raw materials. an adjacent airfield with runways capable of handling fully loaded bombers taking off for delivery flights. 7,000 construction workers attacked the project with urgency driven by war news from Europe. France had fallen in June 1940. The Battle of Britain raged through summer and fall. German submarines were sinking Allied shipping faster than Britain could replace vessels. America wasn't yet at war, but the approaching storm Roosevelt had warned about looked more like an approaching hurricane with every passing week. While construction crews worked around the clock at Willow Run, Sorensen faced a more complex problem than just building a factory. He needed to figure out how to actually manufacture B-24 Liberators using his assembly line concepts. That required understanding the bomber in detail that consolidated sketches and templates couldn't provide. Sorensen had 2 B-24 bombers flown from San Diego to Dearborn, Michigan. Ford engineers completely disassembled both aircraft part by part, measuring everything, photographing every component, documenting every connection and fastener. What they discovered was both encouraging and horrifying. Encouraging because the B-24 was indeed a collection of sub-assemblies that could theoretically be manufactured separately. Horrifying because Consolidated had virtually no proper engineering drawings. The company's blueprints were incomplete sketches, filled with discrepancies and unfamiliar symbols. Critical dimensions existed only in the memories of master builders on the San Diego factory floor. A 1,000-member tool design group worked around the clock, 7 days a week for almost a year, creating proper 3-dimensional engineering drawings of every component. They generated 5 million square feet of blueprints, more documentation than had been produced for any single product in manufacturing history. Those blueprints guided the design of custom machinery that would make mass production possible. 1,600 specialized machine tools, 11,000 fixtures, some 60 feet tall, that would stamp, mill, drill, and grind parts to tolerances measured in thousandths of an inch. The machinery investment alone exceeded what most aircraft manufacturers spent on their entire facilities, but Sorensen understood that upfront investment in proper tooling would be recovered through production efficiency. Building the first B-24 at Willow Run might cost millions. Building the 10,000th would cost a fraction as much per aircraft, because all the complex engineering and tooling development would already be complete. By September 1941, the Willow Run factory stood substantially complete. The assembly line machinery was being installed. Training programs for workers were being developed. Ford engineers had figured out how to break B-24 production into discrete steps that semi-skilled workers could perform after brief training. The first aircraft would roll down the production line within weeks, Sorensen predicted publicly. Ford would be producing B-24s at the rate of 1 per hour by mid-1942. America's bomber production problems were solved. He was wrong on every timeline. The next 2 years would prove more difficult, more frustrating, and more costly than anyone at Ford Motor Company imagined. The bomber plant that critics had mockingly nicknamed Will It Run would spend months producing almost nothing while consuming resources and generating national criticism. The collision between automobile manufacturing culture and aircraft production reality would create chaos that threatened to derail the entire program. But in September 1941, with war still 3 months away and confidence running high, Sorensen and his team believed they'd revolutionized an industry. They'd designed the factory, they'd created the tooling, they'd developed the training programs, they'd solved the theoretical problems. All that remained was proving it would actually work. The demonstration would begin on December 7th, 1941, when events at Pearl Harbor transformed bomber production from an interesting engineering challenge into a matter of national survival. December 8th, 1941. The morning after Pearl Harbor, Charles Sorensen walked through Willow Run's vast factory floor with a weight pressing on his chest that had nothing to do with the Michigan winter, cold seeping through gaps in the building's incomplete walls. Japan had crippled the Pacific Fleet. America was now at war with both Japan and Germany, and the world's largest bomber factory had yet to produce a single combat-ready aircraft. The pressure transformed overnight from corporate ambition to national emergency. Every day, without bombers rolling off Willow Run's assembly line, if you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Was another day America fought with inadequate air power. Every delay meant more sailors drowning in the Pacific, more soldiers dying in places most Americans couldn't find on a map, more time for enemies to consolidate their conquests. The phone calls from Washington began immediately. When would production start? How many aircraft per month could Ford guarantee? Could the schedule be accelerated? The questions came from generals who needed bombers yesterday, from politicians facing a terrified public, from procurement officers trying to allocate resources among competing emergencies. Sorensen's answers were honest but unsatisfying. The first B-24 would leave the factory in months, not weeks. Initial production would be measured in dozens of aircraft, not hundreds. The 1 bomber per hour target remained the goal, but achieving it would take time to work out the inevitable problems. Those problems began revealing themselves immediately. The first issue was one Sorensen had anticipated but underestimated. Consolidated Aircraft, which designed the B-24, maintained design authority over the aircraft. Every change Ford wanted to make to improve manufacturability required Consolidated's approval, and Consolidated, protective of its design and skeptical of Ford's mass production approach, approved very little very slowly. Ford engineers would identify a way to simplify a component for easier assembly. Consolidated's engineers would reject the change, arguing it might affect aircraft performance. Weeks would pass in technical disputes, while the assembly line sat idle waiting for resolution. The bureaucratic friction between traditional aircraft culture and mass production philosophy created constant delays. Worse still, Consolidated kept modifying the B-24 design based on combat experience from European and Pacific theaters. These modifications were necessary improvements that made the bomber more effective and survivable. But each change meant Ford had to retool machinery, revise assembly procedures, and retrain workers. In January 1942 alone, the Army Air Corps issued 47 engineering change orders affecting B-24 production. Some were minor, many were not. Installing self-sealing fuel tanks to prevent fires when hit by enemy rounds required redesigning the entire wing structure. Upgrading defensive armament meant new turret systems and reinforced mounting points. For traditional aircraft manufacturers building a few aircraft per month, incorporating these changes was manageable. For Ford, attempting to establish mass production, every change was catastrophic. The assembly line philosophy required absolute standardization. Build the same thing the same way repeatedly until the process became perfectly efficient. Constant design changes made standardization impossible. Sorensen had designed the factory around hard steel dies, the same type used to stamp automobile body panels. These dies were expensive but durable, and could produce thousands of identical parts with minimal variation. The problem was that aluminum, which comprised 35% of the B-24's structure, was far softer than automobile steel. The hard dies damaged and defaced the aluminum parts they were supposed to shape. Thousands of components had to be scrapped. The dies themselves had to be completely redesigned using softer materials. Millions of dollars of tooling investment was thrown away and rebuilt. Months of production time evaporated, while engineers figured out how to properly work with aluminum at mass production scale. The workforce challenges proved even more difficult than the technical ones. Willow Run was located 30 miles from Detroit, in what had been rural farmland. Workers had to commute from the city on roads inadequate for heavy traffic. Wartime gasoline and tire rationing made the daily commute increasingly difficult. In 1 month during early 1942, Ford hired 2,900 new workers at Willow Run. The same month, 3,100 workers quit. The turnover rate meant Ford was losing ground, despite desperate recruiting efforts. Workers would complete training, work a few weeks, then quit because the commute was impossible or the working conditions were too difficult. The factory itself contributed to the problem. 3.5 million square feet under one roof created an environment that was often miserable. In summer, the uninsulated metal roof turned the factory into an oven. Temperatures on the assembly line floor reached over 100 degrees. In winter, the heating system struggled to warm the enormous space. Workers wore heavy coats while assembling bombers. The scale of the building meant workers often walked a mile or more from the parking areas to their workstations. The cafeteria served thousands of meals per shift, but had seating for only a fraction of the workforce. Many workers ate standing up or sitting on the floor. The bathrooms, placed at the building's edges to simplify plumbing, required 10-minute walks from many work stations. Henry Ford himself created additional problems. The company's founder, now 78 years old and increasingly erratic, remained violently opposed to labor unions. The United Auto Workers had fought bitter battles to organize Ford's automobile plants. Now they sought to organize Willow Run. Ford's response was characteristically stubborn and self-destructive. He resisted unionization with every tool available, creating labor tensions that erupted into strikes and slowdowns. Workers already frustrated by difficult conditions and inadequate pay found themselves in constant conflict with management. Adding to the chaos, Henry Ford initially refused on principle to hire women for production work. This was insane given that military conscription was draining away male workers by the thousands. But Ford held to his belief that factory work was unsuitable for women until sheer necessity forced him to relent. By mid-1942, women began appearing on Willow Run's assembly lines in substantial numbers. They'd eventually comprise more than 25% of the workforce. Many proved more capable than the men they replaced, particularly for detailed work requiring manual dexterity and attention to precision. But the resistance to hiring them had cost months of production time. The training challenge remained perhaps the most fundamental problem. Traditional aircraft workers spent years learning their craft. Ford's system required training workers in weeks to perform specific limited tasks. The compressed training created quality control nightmares. Workers would complete their brief training and go to the assembly line believing they knew what they were doing. Weeks later, inspectors would discover that entire batches of aircraft contained defective work because the training had been inadequate or the worker had developed bad habits that nobody caught early. A congressional committee visited Willow Run in April 1942 to investigate the program's problems. Senator Harry Truman, who chaired the Senate Special Committee to investigate the National Defense Program, toured the facility and listened to both Ford management's explanations and workers' complaints. Truman's committee issued a report that was devastating in its criticism. Ford Motor Company, the report concluded, had created a production line that too closely resembled an automobile assembly line despite warnings from experienced aircraft professionals. The company's arrogance had produced a facility that consumed enormous resources while delivering minimal results. The criticism was justified by the numbers. By December 1942, more than a year after Pearl Harbor, Willow Run had produced only 56 B-24 bombers. Of those, none were considered combat-ready. All were assigned to training bases, reconnaissance duties, or transport roles. The aircraft had quality problems that made them unsuitable for combat operations. Air Corps Chief General Henry Hap Arnold privately told Charles Lindbergh, who was consulting at the plant, that combat squadrons greatly preferred the B-17 bomber to the B-24 because when we send the 17s out, most of them come back. When we send the 24s out, most of them don't. Arnold wasn't just critiquing the basic B-24 design. He was specifically concerned about Willow Run's production quality. Aircraft built at Consolidated's facilities or at Douglas Aircraft's plant in Tulsa performed adequately, but Willow Run's bombers had recurring problems with structural integrity, system reliability, and assembly quality. The mockery became public and widespread. Will it run? Became the standard joke in aviation circles and among Washington officials. Ford's grand promises had produced a factory that consumed resources without delivering results. The company was a national embarrassment at exactly the moment America needed industrial miracles. Sorensen faced calls for his resignation. Ford's contract with the War Department came under review. Serious discussions occurred about whether the government should take over Willow Run's operation entirely, removing Ford management and bringing in experienced aircraft production teams. What saved the program was a combination of Ford's refusal to quit and the gradual grinding resolution of the accumulated problems. By autumn 1943, multiple factors finally began aligning in Willow Run's favor. First, leadership changed. Sorensen, exhausted and increasingly sidelined in Ford Motor Company power struggles, was replaced as Willow Run's director by Meade Bricker, a more diplomatic manager better suited to working with government officials and aircraft industry partners. Second, Ford negotiated a revised relationship with Consolidated. Rather than attempting to build complete aircraft from raw materials, Willow Run would receive many pre-manufactured sub-assemblies from other facilities. The factory would focus on final assembly and systems integration. This reduced the manufacturing complexity to something more manageable. Third, the government authorized Ford to decentralize production. Many B-24 components would be manufactured at other Ford facilities around Michigan, then shipped to Willow Run for assembly. This relieved pressure on the massive but increasingly chaotic main plant. Fourth, the workforce stabilized. The government built housing near the factory to reduce commute problems. Willow Village, a temporary community of dormitories and small houses, provided housing for more than 15,000 workers and their families. The on-site housing reduced turnover and improved morale. Fifth, and perhaps most importantly, the workers themselves gained experience. The learning curve that afflicts any complex manufacturing operation finally began showing results. Workers who'd struggled to perform unfamiliar tasks in early 1942 had now repeated those tasks thousands of times. Muscle memory replaced conscious thought, speed increased, while error rates declined. The training programs improved dramatically. Instead of generic instruction, Ford developed role-specific training that taught workers exactly and only what they needed for their particular station. A riveter didn't need to understand aerodynamics. A wire harness installer didn't need to know structural engineering. Teach them their specific task perfectly, and trust that the system would produce functional aircraft. By January 1943, Willow Run produced 31 B-24s. By June, 190 aircraft rolled off the line. The numbers were still far below Sorensen's original 1 per hour promise, but they represented real progress. More importantly, the quality problems began disappearing. Combat squadrons receiving Willow Run's bombers reported that aircraft performance now matched or exceeded bombers from traditional manufacturers. The breakthrough came in March 1944. That month, Willow Run produced 453 complete B-24 Liberator bombers in 468 working hours. The arithmetic was simple and stunning. 1 complete bomber every 63 minutes. Sorensen's seemingly impossible promise had become reality. The workers achieved this through a choreography of human and mechanical coordination that resembled industrial ballet. The mile-long assembly line moved continuously. Major assemblies arrived at precisely timed intervals from sub-assembly areas throughout the factory. Wings appeared overhead, suspended from ceiling-mounted cranes that moved in synchronization with the main line. Fuselage sections arrived on rail cars. Engine assemblies descended from assembly fixtures. At each station along the line, workers had between 3 and 8 minutes to complete their assigned tasks before the aircraft moved to the next station. No wasted motion. No hesitation. Every tool positioned exactly where it would be needed. Every part pre-staged and inspected. Station 47 installed the bomb bay doors. Workers had 6 minutes to position the doors, align mounting points, install 42 bolts to specific torque values, and verify that the doors opened and closed smoothly. They performed this task 16 times per shift, 96 times per day. The repetition produced perfection. Station 62 married the wings to the fuselage. This critical operation required perfect alignment and structural connection capable of handling flight stresses. 8 workers, using massive overhead fixtures, had 12 minutes to complete the operation. They did it without verbal communication, hand signals only. The factory's noise level made conversation impossible anyway. The final stations installed systems, connected wiring, tested equipment, and performed acceptance checks. Engines started for the first time, propellers turned, control surfaces moved, weapons systems were tested with dummy ammunition. Fuel systems were pressurized and checked for leaks. At the line's end, pilots from Ford's flight test team climbed into freshly completed bombers and taxied them directly onto the adjacent runway. No transport, no delay. Build the aircraft, test it immediately, fly it to a military acceptance facility. The entire process from raw aluminum sheet to flying bomber took approximately 63 hours. The production rate created logistical challenges nobody had anticipated. Willow Run was producing B-24s so fast that the military couldn't process them quickly enough. Hundreds of completed bombers sat parked on every available space around the airport, waiting for Army Air Corps ferry pilots to deliver them to operational units. At peak production in April 1944, the backup reached 400 aircraft. Ford built them faster than pilots could fly them away. The sight of hundreds of silver bombers parked wingtip to wingtip around Willow Run became iconic. Newsreel cameras captured the scene. Propaganda posters featured it. This was America's arsenal of democracy made visible. The human cost of this achievement rarely appeared in the triumphant news coverage. The workers maintaining the 63-minute production rate worked 2 9-hour shifts, 6 days a week. Exhaustion was constant. Injuries from rushed work were common. The pressure to maintain speed meant safety sometimes took second place to schedule. But the workers understood what they were building and why speed mattered. Every B-24 leaving Willow Run meant more bombs falling on German factories, more submarines hunted in the Atlantic, more supplies delivered to embattled allies. The connection between their welding torch and battlefield victory was direct and visible. Letters from servicemen overseas were posted throughout the factory. Bomber crews wrote thanking Willow Run workers for aircraft that brought them home despite battle damage. These letters mattered more than any management directive. The workers weren't just building bombers, they were protecting the crews who flew them. By mid-1944, Willow Run hit its stride in every measurable way. Production reached 650 aircraft monthly. Quality ratings surpassed traditional manufacturers. Cost per aircraft dropped from $238,000 in early 1942 to $137,000 in 1944, despite inflation and wage increases. The efficiency gains came from relentless optimization of every process. Ford engineers studied each station, timing every motion, eliminating wasted steps. They discovered that repositioning a tool rack could save 3 seconds per aircraft. Multiply that by 16 aircraft per shift, and suddenly you're producing an extra aircraft every week from that single tiny improvement. The prefabrication strategy reached its ultimate expression. Sub-assemblies arrived at the main line as complete as possible. The center wing section came with fuel tanks installed, fuel lines plumbed, control cables routed, and structural connections pre-drilled. Workers on the main line simply positioned it, bolted it to the fuselage, and connected a handful of quick disconnect fittings. What had taken days in traditional aircraft factories took minutes at Willow Run because all the time-consuming detailed work happened in sub-assembly areas where workers could access components easily without crawling through a partially assembled fuselage. The contrast with German bomber production became stark and strategically decisive. Germany's aircraft industry, damaged by Allied bombing and strangled by resource shortages, struggled to maintain production levels. Luftwaffe bomber strength peaked in early 1943 and declined steadily thereafter. Meanwhile, American bomber production soared. Willow Run alone was producing more bombers monthly than Germany's entire aircraft industry could manage. Add in B-17 production at Boeing, Douglas and Lockheed facilities, plus medium bomber production at other plants, and the production gap became an unbridgeable chasm. German fighter pilots reported the psychological horror of the numbers. They'd shoot down American bombers, watch them fall, feel momentary victory, then see another formation appear on the horizon, and another behind that, and another behind that. The Americans had bombers to spare. Germany didn't. By the time the war in Europe ended in May 1945, Willow Run had produced 8,685 B-24 Liberator bombers. Ford also manufactured 1,893 knockdown kits, complete sets of pre-manufactured components shipped to other factories for final assembly. The grand total approached 10,000 complete bombers from one facility, the B-24, produced at multiple plants by multiple manufacturers, became the most produced heavy bomber in history. Total production across all facilities reached approximately 18,482 aircraft. Willow Run's contribution represented almost half of all B-24s built. One factory, using techniques developed by a man who'd never built an airplane, produced as many heavy bombers as all of Germany's aircraft factories combined produced fighters during the same period. The Luftwaffe built approximately 30,573 Messerschmitt Bf 109 fighters during the war years. They built approximately 20,068 Focke-Wulf 4190 fighters. Combined German fighter production totaled around 50,000 aircraft, but fighters and bombers weren't equivalent. A B-24 carried 10 men, 8,000 pounds of bombs, and enough fuel to strike targets 1,000 miles away. It required 4 times the aluminum of a fighter, 10 times the man-hours, 20 times the manufacturing complexity. One B-24 rolling off Willow Run's line represented roughly the industrial investment of 4 German fighters. By that measure, Willow Run's production alone matched roughly 1/3 of Germany's entire fighter production in terms of manufacturing capacity consumed. The strategic implications were crushing for Germany. Every resource invested in fighters was a resource not available for bombers. Every pilot trained as a fighter pilot was a pilot not flying reconnaissance or transport or ground attack missions. Germany's industrial capacity forced impossible choices. America's capacity made every choice possible simultaneously. May 7, 1945. Germany surrendered unconditionally. The war in Europe ended. And at Willow Run, the bombers kept rolling off the assembly line with mechanical indifference to the celebration erupting across America. The factory operated on momentum now, completing contracts already in progress, while everyone knew the end was approaching. By late May, the government officially terminated Ford's B-24 contract. Production would continue through June to complete aircraft already in the pipeline, then cease entirely. The largest aircraft factory in the world would close after just 3 years of operation. On June 28, 1945, the final B-24 Liberator rolled off Willow Run's assembly line, serial number 44533690. The workers simply completed their tasks one last time, then began the process of shutting down the machinery that had produced 8,685 bombers. By December 1945, employment at Willow Run had fallen from 42,000 workers at peak production to fewer than 7,000. Most were engaged in shutdown operations, preserving machinery, cataloguing equipment, preparing the facility for whatever came next. The massive building stood largely empty, its concrete floors echoing with absence. The human stories behind those employment numbers rarely made headlines. Workers who'd spent 3 years building bombers suddenly faced unemployment. The women who'd proven themselves capable on the assembly line were told their services were no longer needed. Men returning from military service wanted their jobs back. Rosie the Riveter could go home now. Thanks for the help. Some workers had relocated entire families to Michigan, drawn by the promise of war production employment. Now they faced difficult choices. Return to wherever they'd come from, hoping to find work, stay in Michigan and compete for limited peacetime jobs? The transition from wartime to peacetime economy created dislocations that affected millions. But if the workers' stories faded quickly from public consciousness, the factory's legacy proved more durable. Ford Motor Company declined to exercise its option to purchase Willow Run from the government. The company wanted to focus on automobile production, not maintain a massive facility designed for purposes that no longer existed. In 1946, Kaiser Frazer Corporation, a partnership between shipbuilding magnate Henry J. Kaiser and automobile executive Joseph Frazer, purchased the plant. They would use it to manufacture automobiles, bringing the facility full circle back to its roots in automotive production. Kaiser Frazer built approximately 739,000 cars at Willow Run between 1947 and 1953. The production never matched wartime intensity, but it demonstrated that the facility could be adapted to peacetime purposes. When Kaiser Frazer failed in 1953, General Motors purchased the plant and used it for transmission production until the company's bankruptcy in 2009. The physical legacy of Willow Run gradually disappeared. Most of the original building was demolished in the years following GM's bankruptcy. A small section survives as a museum, preserved by groups who recognized the historical significance of the site. Visitors can stand in what remains of the factory floor and imagine the choreographed chaos of 16 bombers being assembled simultaneously on the mile-long production line. But the true legacy of Willow Run existed not in buildings or machinery, but in the demonstration of what mass production could achieve when applied to previously craft-based industries. The principles Charles Sorensen sketched on hotel stationery in January 1941 became foundational concepts in manufacturing worldwide. The breaking of complex products into sub-assemblies that could be manufactured simultaneously. The standardization of components to enable interchangeability. The use of specialized workers performing specific tasks repeatedly rather than requiring generalists with comprehensive skills. The investment in custom tooling and fixtures that enabled precision at scale. The relentless optimization of every process to eliminate wasted motion and time. These weren't new concepts. Ford had pioneered them for automobile production decades earlier. But Willow Run proved they could be applied to any manufacturing challenge, regardless of complexity. If you could build bombers on assembly lines, you could build anything. The post-war aircraft industry absorbed this lesson thoroughly. When Boeing developed the B-52 Stratofortress bomber in the 1950s, the design emphasized manufacturability from the beginning. When commercial jet aviation exploded in the 1960s, Boeing and Douglas built aircraft using assembly line principles derived directly from wartime bomber production. The influence extended beyond aviation. Shipbuilding, which had been revolutionized by Henry Kaiser's Liberty ship program, continued using prefabrication and modular assembly techniques. When Japan and South Korea rebuilt their shipbuilding industries in the 1950s and 60s, they studied both Kaiser's ships and Willow Run's bombers, applying those lessons to create the most efficient shipyards in the world. The housing industry eventually adopted similar approaches: prefabricated homes, modular construction, standardized components, all drew on principles proven at Willow Run. The construction of massive post-war housing developments like Levittown used assembly line logic applied to residential construction. Even industries with no obvious connection to bombers or automobiles found lessons in Willow Run's story. The breaking of complex tasks into simple, repeatable steps became fundamental to operations management theory. Business schools taught case studies about Willow Run's transformation from chaos to productivity, analyzing what worked and what failed. The training methodology developed at Willow Run influenced vocational education for decades. The insight that workers didn't need comprehensive understanding of an entire product, only mastery of their specific task, enabled rapid workforce development in multiple industries. This democratization of skilled work had profound social implications. Before Willow Run, aircraft manufacturing was a guild system where expertise passed from masters to apprentices over years. Entry required connections or exceptional persistence. The work paid well but remained closed to most people. Willow Run proved that ordinary people could produce extraordinary products with proper training and organization. The 42,000 workers at peak production included former farmers, store clerks, housewives, labourers, anyone willing to learn. More than 25% were women. Thousands were African American, employed in skilled positions that would have been closed to them in peacetime industry. The mixing of people from different backgrounds, different regions, different life experiences created a cultural impact that extended beyond the factory. Workers who'd never imagined building aircraft discovered capabilities they didn't know they possessed. Women who'd been told factory work was unsuitable for them proved more capable than many men at detailed precision tasks. Minorities who faced discrimination everywhere else found that production lines judged workers solely on output, not skin color. These experiences didn't automatically translate into post-war social progress. Many of the gains were rolled back as soldiers returned and women were pushed out of industrial work. Discrimination resumed in most industries. But the demonstration that traditional barriers were artificial rather than natural planted seeds that would eventually grow into broader social change. The veterans who'd flown B-24s built at Willow Run carried their own perspectives on the factory's legacy. For them, the statistics of production meant something more personal than industrial achievement. Every bomber represented a crew that might survive a mission that would have been impossible without adequate aircraft. Bomber crews over Germany and Japan faced horrifying casualty rates. Entire squadrons were lost in single missions. Aircraft were shot down, blown apart, or crippled so badly they couldn't return to base. The men who flew these missions understood viscerally that their survival depended on having enough replacement aircraft. If your bomber was damaged beyond repair, you needed a replacement immediately. If your squadron lost 3 aircraft in a mission, you needed 3 replacements. The mathematics of attrition warfare meant that the side which could replace losses fastest would eventually win regardless of tactical outcomes. Willow Run's production rate meant American bomber crews could take losses that would have been strategically crippling for Germany. Losing 10 bombers in a mission was tragic for the 100 men killed or captured, but operationally, 10 replacement bombers would arrive within days. The strategic bombing campaign could continue. German bomber crews had no such assurance. Luftwaffe bomber production never recovered from Allied attacks on aircraft factories. By late 1944, Germany was producing fewer than 200 bombers monthly. A single bad month of combat losses could cripple operational strength for months afterward. The strategic impact became visible in the contrasting air campaigns. American and British bombers struck German targets relentlessly despite heavy losses because replacement aircraft arrived constantly. German bombers, after early war successes, largely disappeared from European skies because replacements couldn't match attrition. This disparity reflected the fundamental difference between craft production and mass production at industrial scale. Germany's aircraft industry produced technically superior aircraft in many cases. The Messerschmitt Bf 109 and Focke-Wulf F-Turf 190 were excellent fighters. German jet aircraft were years ahead of Allied designs, but technical superiority meant nothing when you couldn't produce enough aircraft to matter. The Luftwaffe might win individual battles through superior equipment and tactics. America would win the war through superior production and logistics. Quality couldn't overcome quantity when the quantity gap reached orders of magnitude. The psychological impact on German military planners became evident in captured documents and post-war interviews. They'd understood American industrial capacity theoretically. Intelligence estimates had predicted massive production increases, but understanding the numbers intellectually differed from confronting the reality of endless bomber streams. German fighter pilots reported that shooting down American bombers felt increasingly futile. Success in combat didn't translate to strategic progress because the bombers just kept coming. Some pilots compared it to fighting the ocean. You could bail water frantically, but the ocean didn't care. There was always more water. This was precisely the strategic effect American planners had intended when they'd commissioned bomber production in 1940. Overwhelm the enemy through sheer industrial output. Make victory inevitable through mathematics rather than heroics. turn warfare into an accounting problem where the side with larger resources would eventually exhaust the side with smaller resources. Willow Run embodied this philosophy perfectly. The factory was a machine for converting raw materials and labor into strategic air power faster than enemies could destroy that air power. Every 63 minutes, another bomber. Every day, another 16 bombers. Every month, another 650 bombers. The numbers accumulated into an insurmountable advantage. Charles Sorensen, whose hotel stationery sketches had started this entire program, lived to see the vindication of his vision, but received little public recognition for it. He'd left Ford Motor Company in 1944 after internal power struggles that had nothing to do with Willow Run's success. Henry Ford's grandson, Henry Ford II, was consolidating control of the company and removing executives loyal to the elder Henry Ford. Sorensen's departure meant he wasn't present when Willow Run hit peak production. He wasn't there when the war ended. He wasn't there when the final bomber rolled off the line. The factory's triumph belonged to Meade Bricker and the thousands of workers who'd actually achieved what Sorensen had envisioned. But history has slowly corrected that oversight. Modern manufacturing historians recognize Sorensen as one of the key figures in developing mass production theory. His work on the Model T assembly line in 1913 had revolutionized automobile manufacturing. His work on Willow Run proved those principles could scale to any product regardless of complexity. The contrast between Sorensen's vision and the aviation industry's skepticism provides one of history's clearer demonstrations that expertise can become a barrier to innovation. The aircraft manufacturers, who dismissed Ford's ambitions as impossible, weren't stupid or incompetent. They were applying decades of experience to reach their conclusions. Their expertise told them that aircraft were too complex for mass production. Their experience showed that constant design changes made standardization impossible. Their knowledge of materials and processes indicated that automobile techniques wouldn't work for aviation. They were wrong about everything because their expertise was grounded in craft production assumptions that mass production principles would render obsolete. Sorensen's advantage was his ignorance of aircraft manufacturing traditions. He didn't know why things couldn't be done a certain way, so he tried anyway. This wasn't random luck. It was a systematic application of proven principles to a new problem, unencumbered by assumptions about what was possible. The lesson extends beyond manufacturing. Disruption often comes from outside industries, precisely because outsiders don't know what's supposedly impossible. They question assumptions that insiders accept without examination. They apply principles from other domains without realizing they're violating conventional wisdom. This pattern would repeat throughout industrial history. Toyota's lean manufacturing revolution came from applying American production principles that American companies had abandoned. The personal computer revolution came from hobbyists who didn't understand why computers had to be room-sized mainframes. The Internet transformation came from academics and researchers who didn't know why networking had to be controlled by telephone monopolies. Willow Run's story fits this pattern perfectly. An automotive production expert applied automobile techniques to aircraft manufacturing, succeeded despite industry-wide skepticism, and in the process transformed how aircraft would be built forever after. The final accounting of Willow Run's impact requires comparing inputs to outputs across multiple dimensions. The facility cost approximately $200 million to build and equip, an enormous sum in 1941 dollars. It consumed millions of tons of aluminum, steel, and other materials. It employed 42,000 workers at peak production. Those inputs produced 8,685 complete bombers, plus component sets for nearly 2,000 more aircraft assembled elsewhere. Each bomber could deliver 8,000 pounds of bombs to targets 1,000 miles away. Each bomber carried 10 men who'd been trained at enormous expense and whose lives depended on their aircraft's reliability. The strategic value of those bombers can't be calculated purely in monetary terms. How much was control of German airspace worth? How much value should be assigned to destroying German industrial capacity? How much did the bomber offensive contribute to shortening the war? Military historians debate these questions endlessly. Some argue strategic bombing was less effective than its advocates claimed. Others contend it was decisive in crushing German war production. The truth likely falls somewhere between these positions. What's undeniable is that American bomber production vastly exceeded German capacity to defend against it. By late 1944, Allied bombers attacked German targets with near impunity. Fighter losses among bomber escorts declined as Luftwaffe fighter strength collapsed. The tonnage of bombs dropped, increased exponentially, while losses decreased proportionally. This shift reflected both improvements in Allied tactics and the simple mathematics of attrition. Germany couldn't replace aircraft and pilots fast enough to maintain effective defense. America could afford losses that would have been catastrophic for Germany, because Willow Run and facilities like it ensured replacements always exceeded losses. The human cost on both sides was staggering. Allied bomber crews suffered approximately 40% casualty rates over Europe. German fighter pilots faced even worse odds as the war progressed. Civilians in bombed cities died by the hundreds of thousands. The strategic bombing campaign was brutally effective and brutally expensive in lives, but warfare, particularly industrial warfare on the scale of World War II, ultimately came down to resource competition. The side that could sustain losses while maintaining combat power would defeat the side that couldn't. Willow Run's contribution to that equation was providing the sustainable production that made attrition warfare winnable for America. The final B-24 built at Willow Run was delivered to the Army Air Corps and immediately placed in storage. The war had ended. Nobody needed more bombers. Within 2 years, most B-24s were sent to scrapyards. Their aluminum was melted down and repurposed for peacetime products: coffee percolators, toasters, pots and pans, consumer goods to satisfy peacetime demand. This transformation from weapons to consumer goods symbolized America's larger transition. The industrial capacity developed for war would be redirected to peacetime prosperity. The workers who'd built bombers would build automobiles and appliances. The factories that had produced weapons would produce washing machines and refrigerators. The remarkable thing was how quickly this transition happened. Within months of war's end, American industry was converting to peacetime production. Within 2 years, consumer goods were abundant again after years of wartime shortage. The same industrial system that had overwhelmed enemies through production volume now overwhelmed domestic markets with consumer products. Willow Run's story became part of American mythology about World War II, the greatest generation, the arsenal of democracy, the home front contribution to victory. These narratives emphasized American unity, determination, and industrial might. They were true, but incomplete. The complete story includes the labor disputes, the quality problems, the discrimination that persisted despite wartime necessity, the cynical profiteering alongside genuine sacrifice. Willow Run's workers weren't superhuman. They were ordinary people who achieved extraordinary things because the system organized their efforts effectively and gave them work that felt meaningful. The meaningfulness mattered more than many histories acknowledge. Workers tolerated difficult conditions, long hours, and repetitive work partly because they understood their contribution to the war effort. Every bomber represented protection for someone's son, brother, husband. The connection between factory work and battlefield survival was direct and visible. When that connection disappeared in peacetime, so did much of the motivation that had driven wartime: productivity. Post-war labor relations at Willow Run and other defense plants turned contentious as workers demanded better treatment without the national emergency justifying sacrifice. This wasn't ingratitude. It was recognition that employers had profited enormously from the war while workers' gains remained limited and temporary. The broader legacy of Willow Run exists in every modern factory, every assembly line, every manufacturing process that uses principles refined during wartime production. The specific technology has evolved dramatically. Robots now perform tasks that humans did in 1944. Computer systems track production with precision impossible then. But the underlying philosophy remains identical. Break complex products into manufacturable sub-assemblies. Standardize components for interchangeability. Use specialized processes performed by workers or machines optimized for specific tasks. Invest in tooling that enables precision at scale. Optimize relentlessly to eliminate wasted time and motion. These principles, proven at Willow Run under wartime pressure, became the foundation of modern manufacturing. Every efficiency improvement, every production innovation, every breakthrough in manufacturability traces intellectual lineage back to factories like Willow Run, where necessity drove innovation at unprecedented pace. The building is mostly gone now. The workers are nearly all deceased. The bombers were scrapped decades ago. But what they proved together endures. Industrial capacity, properly organized, can overcome apparently insurmountable challenges. Ordinary people, given training and purpose, can achieve extraordinary results. Production volume, sustained over time, can be more decisive than tactical brilliance or technological superiority. These lessons matter beyond military contexts. They apply to any large-scale challenge requiring sustained effort and massive resource mobilization. Climate change, pandemic response, infrastructure development, space exploration. The problems differ, but the principles remain constant. Willow Run demonstrated that America could accomplish seemingly impossible industrial tasks when necessity demanded it. The factory existed for only 3 years, but in those 3 years, it produced roughly half of all B-24 Liberator bombers built worldwide. 8,685 aircraft, one complete bomber every 63 minutes at peak production. The statistics are impressive. The human story behind those statistics is more impressive still. 42,000 workers, most with no aircraft manufacturing experience, proved that determination, organization, and proper training could overcome every expert's declaration that something was impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.